Okay, all right. So here's what we were talking about. We were talking about vector fields. We saw some physical examples of situations where at every point in space it's natural to associate a vector. And just a quick reminder, gravitational forces, I'm going to say, are such a situation. Anywhere you are near planet Earth, at any such point, there is a corresponding gravitational force vector. So altogether, this forms the gravitational field, they call it. Likewise with electric charges. Fluid flows are another similar situation. The air in this room, for example, is moving a little bit, right? And so, any particular location at that little point right there where I'm pointing, for example, the airflow maybe is something like this. Right? You can associate a vector at that point. And so the flow of air in this room can be represented by a vector field, for example, using the velocity to describe the airflow at that point. Okay, all right. So with those physical examples in mind, here's the definition we're going to make. A vector field on Rn. It looks weird to write it this way, but it's a function from Rn to Rn. And I was uncomfortable with this when I first saw it as well, but it makes loads of sense if you just interpret it the right way. Now, here's how you're thinking, perhaps. Here's a function from R2 to R2, for example, and we're accustomed to thinking of the domain as being over here and the target being over here. For example, when we use change of variables. Right? So this is a change of variables function as I've got it drawn here, where I interpret the inputs as points and the outputs as points specifically. The big idea of interpreting this as a vector field instead is simply interpreting the input, yes, still as a point, right? But interpret the output as being a vector. Drawn with its tail at that input point just to clearly associate it to being, that's the output vector corresponding to that input point. Okay. So it is still, again, you look at this input point, that point comes out of R2 because we have this picture drawn in R2. The output, vector is a vector in R2 also. Just thought of as a vector. Okay. Alrighty. So, I guess we've already seen a bunch of examples, but let me, using this algebraic notation, let's see this vector field right here. F of xy is 2, 1. Notice this is a function from R2 to R2. Right? We've got 2 input variables, 2 output variables. Okay. Specifically, the input variables are x and y, describing location. The outputs, the field vector that I associate to any point x, y in the domain here. The field vector that I associate is the field vector 2, 1, and that's a really easy picture to draw. That's this one right here. At any point x, y. We associate the field vector 2, 1. So at that point, I'm going to draw the arrow representing the vector 2, 1. And likewise for every other point, again, this is a constant vector field, and so that's convenient. At every point, you just draw this same associated field vector. Okay. All right. Here's another one. Let's look at this one here. F of x, y equals x, y. Now, all right. So, I guess you could call this the identity vector field or something, right? It's the vector field where the field vector is the same as the position vector. Okay. What does that look like? Again, drawing in this sense, right? What does this vector field look like? The way we understand vector fields to look. Well, at the point x, y. I have a field vector. The formula for that field vector is that the field vector is the same as the position vector. Let's keep that in mind as we draw our picture. Here it is. And notice the picture that I have drawn here at every point, keep in mind points have position vectors, right? The field vector is the same as the position vector for that point. Everybody see what I'm talking about? So it's kind of a weird, this isn't exactly what we are, I don't know, this seems a little surprisingly complicated picture. It's, it's radial and it's magnifying or something, and it doesn't somehow seem quite right, given that the formula for this vector field is so simple. But anyway, that's what it is. Let me note, by the way, to this feeling of unexpectedness, that this kind of a picture that we're looking at, one of the reasons our results are unfamiliar is because this is a brand new way to visualize a function. Right? Remember, this is something I went on and on about back in Chapter 2, all that not only are there different ways to draw pictures that describe functions, but it's really important to understand the differences to, consciously, make a point of seeing those differences, because the calculus of the functions looks different in each picture. Right? So the calculus of graphs is very, very different from the calculus of level sets. We talked about that in detail long ago. So along those lines, this is like our fifth way to visualize a function. We have graphs, we have level sets, we have images, parameterizing. Right, so that's three. Those are kind of the three big ones that we've talked about by name. Let's not forget this one. I tend to think of this as being the natural way to visualize a function. Functions have a domain. There it is. Functions have a target. There it is. You can see the function in this, representing it in this way, moving you from the domain to the target. So, let's call this the natural picture of a function. So that's 4, and here's the 5th. This is none of those previous things. Right? So we have to be open-minded to the fact that, we have a whole new sort of intuition to develop of, given a formula, what does that, look like in the way that we visualize vector fields. We have a totally new picture, kind of category of pictures. Okay, one more example. Here's one more. The position vector x comma y. The associated field vector is negative y comma x. Now that's not it's not the same, but I will point out two things. The field vector has the same length as the position vector. They both have magnitude square root of x squared plus y squared. Right? Furthermore, the position vector and the field vector are perpendicular. And again, easy observation. Dot product is clearly 0. Right? So, let's draw any picture we can think of that satisfies these two observations. The field vector has the same length, but it's perpendicular to the position vector. And here's one. So at a point like this one, for example, keep in mind that being a point, it has a position vector. There's the position vector for that point. The field vector has to have the same length as that, and but be perpendicular to it. And for example, it looks like I didn't draw this I didn't achieve the same length goal very well. But there you go. In green, we have a vector that's perpendicular with the same magnitude. Artistic incompetence aside. And you keep doing that at a bunch of other points. It's not hard to persuade yourself you're going to get a picture that looks like this. And it's like the fluid is sort of rotating around or something. It's like a stirred pot. An example of a vector field that's somehow easier to visualize physically from a fluid's point of view than from a force's point of view. All right. I will point out we could have gone the other way. I mean, how did I know that this thing was going what I'm going to loosely call going counterclockwise? It could have gone clockwise. I mean, for example, what about this? That has the same length and is perpendicular to the position vector. How come I know this isn't going that way? And that's just kind of a plug it in situation. You just come over here to your formula and pick a specific point. Like if you plug in 1, 0, you clearly get 0, 1 as the field vector. And so at this point, 1, 0, field vector is 0, 1. Not 0, -1. So, there you go. How we doing? Is everybody happy? Okay. All right. So the reason we brought up vector fields is because those are going to come up significantly in this next kind of integral we're going to develop. By the way, let's take count. How many kinds of integrals do we know just to keep track? Right? We know single variable integrals. Then there's a very different thing called a double integral. Another very different thing called a triple integral. They have a lot in common. There's a pattern, strong analogies, but these are different kinds of Riemann sums that apply in different situations. We then developed scalar line integral. That's different. And then scalar surface integral. That's different. So we've currently got 5 kinds of integrals. We're about to develop number 6. Like all of our previous integrals that we've developed, this is going to come out of asking a certain kind of a question. A certain kind of a question that we're going to ask is going to lead to an algebraic construction. That algebraic construction is going to be kind of vaguely similar to, but importantly different from, other Riemann sum constructions that we've written down. And so we're going to give it a name and a notation and call it a new kind of integral. Okay. So, here we go. Here's the problem we're going to address. The question is, how do I compute work? Now, y'all remember work from chapter 1. We talked about work. If you want to move, if you displace like this along a straight line, displacement being d, and if the force that you exert as you move along there is this constant vector force F, then we've seen that work is equal to force dot displacement. And I'll refer you back to chapter 1 for a full discussion about that. So I hope everybody remembers that. A quick reminder of what work is. Work is has units of energy. Work is energy, in fact. The word work simply refers to energy in a certain context. It refers to, how much energy does it take to perform a task? So in that context, they call it work. But let's not be confused. Work is, in fact, just energy. And energy is as units of force times distance. Okay. Right. So here's the harder problem that we want to address now. What if I am not moving along a straight line? What if I am instead moving along a curve? Like that. How does that change things? It's not immediately obvious how you deal with that, right? What if likewise the force that I'm applying is not constant? Now you can see I have a bunch of arrows drawn here representing non-constant forces. I'm drawing here, by the way, forces that are opposing your motion. So this is, let's say, maybe the gravitational field that is applying to you. And then you have to apply an opposing force to keep from falling over. Right. So there's a little bit of a distraction, but there is a minus sign that you always have to be on the lookout for. The force that you exert here. I'm going to hold up this stylus. There are 2 forces in play on this stylus. There's the force that I'm applying to keep it from falling, and then there's the force that gravity is applying to it, right? And notice that those forces are exactly the opposite. I know they're exact opposite forces because the sum of those forces is clearly 0 because the pencil is not accelerating. Okay, so we have these opposing forces. Just be careful for this. Always be on the lookout for, wait a minute, which one of these have I been given? Have I been given the force that I need to apply and therefore the force that's relevant to my work calculation? Or have I been given the force that I am working against? in which case I need to put a minus sign to get the work that I am applying, and therefore that's relevant in my force calculation. Okay. All right. So the forces that I'm moving against are like this, and they're not constant. They're different at different places along the path. Right, so the forces that I am applying as I go along here, I'm applying that force along in there, that force along in there, that force along in there, maybe something more like that over there. If the force is not constant, how do you deal with that? All right. So the answer, no surprise. I've already kind of given away the game and said this is going to end up being an integral. Y'all know integrals are Riemann sums. Riemann sums, all Riemann sums, chop it up, add it up. Right? So we're going to take this domain and we're going to chop it up into little pieces, and then we're going to reconsider the question individually on each little piece of the domain. So, for example, here is a little piece of my domain, tiny, teeny, weeny little piece of the domain that I've chopped it up into. There's going to be a little bit of displacement. There's a displacement vector along that piece of the domain. And now, by the way, quick appeal, if I chop small enough, these pieces are approximately little straight lines. So we're kind of, round off errors aside, we are approaching the question we already know an answer to, namely if you're moving along a straight line. The vector fields that I'm working against, again, on this very small scale, the vector field that I am opposing is approximately constant. No, not exactly, but again, round off errors go away in the limit. Right? So the amount of force that I am applying, therefore, is approximately, oh my gosh, that was incompetent. Let's try that again. Amount of force that I'm applying is approximately constant along that whole displacement. So on each little piece of curve, it's an easy question. It's force dot displacement, just like in chapter 1, on each little piece of the curve. Right? And I just have to add that up over the whole curve. So the grand total amount of work, chop it up, add it up. Right? So chop it up, add it up. On each little piece, work is force dot displacement. We just got through talking about how the displacement is a roughly straight line displacement along the curve, and the force that I'm applying. Don't forget that little minus sign in here. In this case, that minus sign because of the opposition. And here you go. We have ourselves a kind of a integral looking thing, right? This work calculation ended up being this Riemann sum like expression, and it's tempting to look at this and say, okay, well let's just it's got to be one of our existing integrals. But it isn't. It's kind of like an integral. It's chop it up, add it up. We have a limit of a sum. There is a kind of an integrand sort of a thing here, appropriate to the application. But this thing here doesn't really anymore represent size exactly. This represents, not only length, but it also represents direction. That is a vector. That is very importantly a vector. The vector aspect of that, what I'm going to call differential, is critical to how this dot product works. This is a very importantly different expression. And likewise, this integrand, that's not a scalar, like it has been in every previous kind of integral that we've seen. Right? So what we have is something that's kind of like our existing Riemann sums in important ways, but also different in important other ways. And so we're just going to give it a name. We're going to call it a new kind of an integral. This thing, it's an integral over a curve, so we're going to call it a line integral just like we have before. To make the distinction, because of the fact that these are vectors in here, I'm going to call this a vector line integral. instead of a scalar line integral. So there's that distinction that I sort of foreshadowed last time or the time before. Okay. The notation, I think, is very plausible. I'm going to abbreviate delta x vector with dx vector, right? I mean, wouldn't that have been your guess? That's following the pattern of what we've done in every context in the past. The integrand, again, you kind of bring it along for the ride. Limit of a summation, well, that's integral symbol. Domain is a subscript, just like with scalar line integrals we've already defined. This notation is, I want to say, pretty much exactly what you would expect. Everybody on board? Okay. All right. So do note in this notation, and I'll zoom in this notation, note also though that the dot product carries over in the notation. You've got to put that dot product in there. It is very important that you are doing a dot of these two vectors. Right? And remember, there is more than one way to multiply vectors. Right? So you can write, v dot w. You can write v cross w. But if you write v w, I don't know which one of these you're talking about. And it is simply not okay to assume that the reader will give you the benefit of the doubt and infer that you are making the correct choice. That's not reasonable, right? So you've got to put that in there. This is not acceptable at all. Okay. All right. Okay, so there you go. We have a new kind of integral. With this Riemann sum written down, let's look back at our specific application. Our specific application, we were looking at that Riemann sum of this form. Our integrand was, you can see it right there, our integrand was negative f. That vector field that we were given was the negative of the vector field that's relevant to our work calculation, and so the integrand is negative f. Okay. All right. Now, here's one of the most, what's the word here? Good news calculations in the course, I think. It goes to the question of computation. Oh my gosh, how are we going to compute these things? We have a new kind of line integral. This is a more sophisticated kind of a line. This has got a vector aspect. We're no longer dealing with familiar, the more familiar, easier objects of scalars and multiplying scalars and doing integrals. Now we're dotting vectors while we're doing integrals. It's like we're doing two hard things at the same time. Surely this is going to be a harder calculation, harder thing to compute. And it turns out, not only is it not harder, it's easier. It's a weird little twist how this happens to work out. But the computation of vector line integrals is even easier than the computation of scalar line integrals. In fact, we already have everything we need to do this. So, what's hard about computing a line integral? Well, line integrals being done over a curve. That's an undesirable domain. We're going to do a pullback, just like we've done before. Again, we've already done pullbacks. We already have this scenario set up. We've already talked about input vectors dt and output vectors dx. Right? We've already got formulas for dx. As we went along the way to computing the ds that we were interested in when we were doing scalar line integrals, right? It was all about the ds. And we were, our punchline was that ds is the magnitude of the dx vector. So we compute dx sort of en route to what we were interested in at that time. Here, we just want the dx. Right? The dx is in the notation here. That's what I need to fit into the integral. That's what I need to pull back. That's what I need a formula for. We already have it. And it's just super convenient. So here it is. dx is v dt. Right? Now, we went through a whole process when we were talking about scalar line integrals, and we, input vector, output vector, applied the derivative transformation, and went through that whole rigmarole to come to that conclusion. I won't reproduce that here because it's the exact same. I mean, literally, it's the exact same scenario, right? It's just that now we don't have to further take the magnitude to get ds. So, it's as simple as that. Your vector line integral, our brand new, seemingly more sophisticated, scary construction. Dx is v dt. Done. It's really convenient. Almost seems a little too good to be true. Sometimes students want to know, hey, what about the stretching factor? Where's the stretching factor? Isn't the idea of a pullback? Isn't stretching factor sort of unavoidably linked into what a pullback is? And, well, not really in this case. Keep in mind, what we really want is to be able to write down the objects that we're interested in. And if you're interested in length, ds, then, yeah, one way to understand, the only way that we could make use of understanding ds in terms of t was to view it as being a multiple, a scalar multiple of dt. That's scalar multiple. We call the stretching factor. Here we're not interested in ds. Here we're interested in dx. So we're going to view it as being a multiple of dt. And there it is. dx is a multiple of dt. You might say that the velocity vector itself is, in this analogy, it's kind of playing the role of the stretching factor. Look, if you like. Anyway, for your consideration. Okay. All right, so there's our result here stated now as a theorem. If you want to compute a vector line integral, as relates to, hey, pick your application. We saw, there are questions as to what other applications will this construction apply to. But if you have a vector line integral, like so, the way to compute it is no problem. Just rewrite dx as v dt, which of course it is. Displacement is velocity times time, old news. And then, by the way, don't forget to plug in the parameterization. X is, of course, a function of t. Got to plug that in too, and that's the pullback. That's all it is. Now, why do I claim this is easier than scalar line integrals? When you're doing scalar line integrals, you have to compute the speed. The speed is your stretching factor. The speed is the magnitude of the velocity. Magnitudes involve using square roots, and square roots are annoying. They make for hard integrals. Right? Here, no magnitude, no square roots. Just a dot product. Dot products are four-function arithmetic. Right? Four-function algebra. Two-function algebra. Right? There's no divisions, there's no square roots. And so you tend to get relatively easy expressions in the resulting integral here. So let's see an example of this working out. Here we go. So we're going to be moving, we're going to walk counterclockwise along the unit circle from 1, 0 to negative 1, 0. Step 1, let's understand our path. Our path is this. You see we're walking counterclockwise along the path from 1, 0 to negative 1, 0. Yeah. Okay. Let's see here now. As we go along that path, the wind necessitates pushing with an opposing force given by that formula. Now let's think about the whole minus sign business. Is this the force that I need to oppose, or is this the force that I am applying to oppose some other force? That's the latter here. It says right here, I am pushing with this opposing force. right? So we don't have to stick in an extra minus sign here the way the problem was phrased. The force that I am applying is straight up given to me. And so when we go, step one in writing down our work, application as write it as an integral. It's of course a Riemann sum. It's of course a vector line integral. It's this vector line integral. The force that I'm given is the integrand, no minus. Okay. You always got to pay really careful attention to the phrasing. And again, this is part of the problem is to interpret the question appropriately. So think that through. That is part of what we're testing on these kinds of questions. Right. Now how do I compute one of these vector line integrals? Well, here's our formula. Vector line integral is computed with that. Everything in here, you will notice, comes from the parameterization. The velocity, right, is the derivative of the parameterization. X of t is literally the parameterization. So step one, parameterize your curve. Here's our curve. How do we parameterize, going from 1, 0 counterclockwise around to negative 1, 0. That's, again, our very familiar unit circle parameterization. We've done that long ago. And that is parameterized by this. Think about your bounds, by the way, carefully. I want to start at 1, 0. T equals 0 gives me the point 1, 0. And then I want to end at the point negative 1, 0, and again, think it through, but pi, t equals pi, gives you negative 1, 0. Okay. All right, so there's your parameterization. And now plug and chug. I mean, it's really all downhill from here. Let's see here. So dx is v dt. V, we just calculated here. V is that vector. So there I'm kind of working on the right side of the dot product, and it's literally plug and chug, right? Take the derivative, stick it in where it says it goes. Right? Now let's see here the parameterization. The parameterization is that. Cosine t comma sine t. That goes into our vector field. Now, careful now, where is our vector field? Our vector field is this formula. F of x, y is negative y comma x. And notice that's what happens here. Right? Negative y. There's y, so there's negative y. And then this is x, because you can see, again, x right there. Okay. All right, so it's just straight up plug and chug. And once you get to this point, now, of course, you notice that everything's in terms of t. Do the dot product, lucky break, the dot product turns out to be 1. This is a first example. I made it work out nice. Right? It won't always work out that nice, obviously. But anyway, in this case, works out great. Notice, no square roots. Big win. Okay. All right. Is everybody happy? Any questions? Feel free. No? Okay. All right. Next result. Let's see here. Suppose we are moving, let's see here. All right. Now, counterclockwise along the unit circle from 1, 0 to negative 1, 0. Oh, same path. Okay. Same path. Sweet. We already know how to parameterize that path. I don't have to reparameterize. It's the same path. Okay, this time the wind necessitates pushing. Okay, so pushing with an opposing force. So this is my opposing force that I'm applying. I don't need to put in an extra minus sign. And that force is x comma y. All right, so we have a different vector field to plug into. But a lot of this calculation is going to be exactly the same because we have the same parameterization, same curve, so same parameterization, same velocity vector. That velocity vector, all the same, right? The parameterization, all the same. The only difference here is that we are plugging into a different vector field f of xy is just xy. Slightly different from before. Right, so that's different. Everything else is the same. Everybody on board? So we end up with a different integral to work out here. Do the dot product. But this time, again, lucky break. Not that lucky. I did this on purpose. But turns out very conveniently. Here, the dot product is a very convenient 0. And so, again, easy integral to work out. Okay, now why is what does this mean? Work is equal to 0, and how could that be? Let's look at the picture. Remember, we're moving along this curve, going in that direction, and our vector field. We've already drawn a picture of that vector field. It is radial outward, and now I appeal to your memory of how circles work and all their symmetries. Excuse me. And these radial outward field lines are always perpendicular to this symmetric, highly symmetric curve that we're walking along. And so every step along the path, every little bit we go, going from there to there, right, our displacement and our field are perpendicular, therefore the dot product is 0, each little step along the way. Visibly clear. Physically, what would this be like? Physically, this would be like, as I walk along this purple curve, I'm having to kind of lean to the right. I got to apply that force leaning to the right, but I'm not going to the right. I'm going that way. If I lean to the right and then just kind of slowly walk along, right? Not really applying any work, and I get to go along the entire curve. Okay. All right. Okay, last example, real quick. Let's see here. This time, same path again. So wrong color. Counterclockwise along the unit circle. 1, 0. Slightly different path. Ending now at 0, 1 instead of 1, 0. So we're stopping there. We're not continuing on. How's that going to change things? Well, it's going to change our parameterization a little bit, specifically in the form of this different ending point implies a different ending value of t. And if you think through in that parameterization, what's the value of t at that point? Well, that's pi over 2. Notice that pi over 2 plugs in to give me that correct ending point. Yeah? Okay, and other than that, let's see, the vector field here is 2, 5, so a different vector field. Different vector field means that it's different in computing f of x of t. It's constant, so who cares about the x of t? F is just 2, 5. That's easy. Right? But again, it gives us a different dot product. So this dot product turns out to be again, easy to write down, but we do get a different integral here. And here you've got to actually do the calculus, take the antiderivative, plug in the bounds, the usual. And here you get 3. That's your answer. Okay. How are we doing? Is everybody happy? Okay. All right. Okay, so we've defined vector line integrals. We've seen it as addressing a physical application, work. Done some examples. We've seen how to compute them, right? So there's another physical application that's really important I want to talk about, and it comes about by reinterpreting what we've written down in terms of the unit tangent vector. So let's just kind of go along with this, and we're going to, in the process of rewriting our algebra, we're going to come up with a different physical interpretation. Okay. All right. So recall this scenario here. Got our curve. We're moving along. We have a velocity vector, v. There is this unit tangent vector that points in that direction. We haven't really done anything with that in a while, actually. But what we've been interested in is the displacement vector dx and its magnitude ds. Okay. So I'm just going to make the observation that looking at this scenario here, and we've got an existing formula for dx, right? Our existing formula for dx is that dx is v dt, and that's true, right? But just now, bear with me. Notice also dx points in the direction of this unit vector and has that magnitude. So it's, if I've got a unit vector direction and if I've got a magnitude, that tells me how to write dx as that product. So dx alternatively could be viewed as TDS. So instead of VDT, we can write it as TDS. Now, why we'd want to do such a thing, not yet clear, right? So let's observe that this is true, and we'll worry later about why we care. Okay. All right, so with that in mind, let's rewrite our integral. Dx, this time, TDS instead of VDT. Okay, I get that. And then I'm going to, for, I don't know, cosmetics, I'm going to redo my parentheses like that. And notice that it's a little bit appealing, actually. I have an integral ds. And then a formula in here for an integrand. Doesn't this look like a scalar line integral all of a sudden? And there's a temptation to say, oh my gosh, well then we've just been kidding ourselves this whole time. This actually is a scalar line integral. And it just we just hadn't carried through the calculation to make that realization. I don't really like that point of view for a couple of reasons. First of all, dx is a very physically natural thing in this problem, right? And there is something really desirable about writing it this way. The other thing is, I make the case that it's not really clear that this really is a scalar line integral. Let me make the quibble. Yes, it's an integral over a curve. Yes, the differential is ds. Yes, it is a scalar valued integrand. All of those characteristics are just like scalar line integrals. But this integrand is not just a function of position. This is not just a function of x. And now I know what you're thinking. You're thinking, well, look, it says right there, that's a function of x, that's a function of x. Isn't this clearly all a function of x? And the problem is that this tangent vector, this unit tangent vector, depends on the curve. So this is an integrand that is not just well-defined uniquely everywhere in space strictly as a function of x. It can have different values at different points depending on, well, which curve are you traveling along? Right? So I think this is a little bit unnatural. My personal point of view on all of this is that this is describing the direction that you are moving on a piece of the curve. I feel like this is part of the differential. I feel like that's the differential, like this. And that this is the integrand. This is independent of the curve. This is all describing little pieces of the curve. And that's the natural way to break it down. So, anyway, for your consideration. Anyway, so having gotten down to this expression, though, can we find some use for this? And yeah, we can. So keep in mind, we know that dot product with a unit vector, and don't forget, t is a unit tangent vector. So dot product with a unit vector is a component. And let's look at this formula then. This formula says, okay, at any given point on this curve, we're going to look at how much the vector field has a component in the t direction. Let's think of this in terms of fluids. That says how much is the fluid flowing, not just overall. No, not just overall. How much is the fluid flowing along the curve? To what extent, my curve is going like this, to what extent is the fluid flowing in that direction? And that, the way components work, to some extent it's going to be flowing along the curve, to some extent it's not going to be flowing along the curve, but there will be that component of how much it's flowing along the curve. And so I view it as, this is saying, overall along the entire curve, if I add up on each little piece how much the fluid is flowing along the curve, per unit length as you go along the curve. This expression here is kind of, in some sense, a total amount that the fluid is flowing along the curve. So that's what I've got written down here. Now, this is very vague language, and it'd be nice if we could give it a more crisp thing. Crisp description, that this is, in the context of fluid flows, this is, and just give it a name. And it is this pre-existing familiar physical concept. Wouldn't that be nice, right? From a forces point of view, work, energy, it's very satisfying, right? So in this situation, things are just turned a little bit around backwards. We're accustomed to having existing physical concepts and then letting the algebra is subservient. The algebra's got to do what it's got to do. We define the algebra by, it just got to fit the concept. Here we have the algebra already. This algebra came to us very naturally in another context. And so we're kind of creating a physical concept to make sense out of this algebraic construction in a new context, right? So it feels a little weird and forced, but this is actually pretty natural. And by the way, as it turns out, this is an interesting thing in the context of fluids. And if a lot of y'all are engineers, as you go through and take engineering classes, if you take a fluids class, you're going to see this. For this reason, being a natural thing, it's important for lots of kinds of calculations. But this is not an engineering class, and so I'm not going to go off in that direction. But we are going to see, however, some fluids point of view about why this is interesting here in this class. Just not right now, and not very much. Okay. All right. Okay. Yeah. Now, computationally, is this a good thing? The fact that I've rewritten our new vector line integral, the fact that I've rewritten it in a form that kind of makes it look sort of like a scalar line integral, new concept, we're rewriting kind of like an older concept, is this good news computationally? And I say no, this is almost irrelevant computationally. And let me just show you how this plays out. If you were to compute sort of, I'll say, brute force from this point of view, you're going to have integral f dot x prime dt. That's our formula for how to compute vector line integrals. Okay. On the other hand, if you were to take a scalar line integral sort of point of view on this instead, right? There's a more familiar, older concept that why don't I compute from our more familiar formulas? Well, you would get integral f dot, okay, let's see, well, t is x prime divided by the magnitude of x prime. That's t. And then times ds. Wait a minute, now what is ds? ds is magnitude of x prime dt. Right? So just making connections here, the dx is that. Right here, the ds is that. The t is that. Okay, so two observations. One is, which calculation would you rather do? I think it's a clear choice. I'd much rather do the one on the left. No square roots, for one thing. Right? The other observation I'll make is you're perfectly obviously going to get exactly the same answers. The only difference between these two calculations is that you are computing a square root that you are then multiplying by and then subsequently dividing by to no effect. So why do it? Right? Everybody see the point here? So from a computational standpoint, it does not make any sense to do that. Why? That's just silly. Yeah? Okay. All right. So anyway, for your consideration. All right. Okay, so let's talk sort of from a summary viewpoint. What have we done? We've defined this notation. This notation here, a couple of things that I like about it. For one, it connects really naturally to one of the main applications, namely it connects really naturally to work. Right? So this is your kind of displacement vector, and this is very literally your force vector, and you can just see in here work equals force dot displacement. So it's very natural from the point of view of a critical application. Here's another thing I like about this notation. It's very compact, right? It's easy to write down. So this is my favorite notation for vector line integrals. If I don't have some sort of other particular motivation, if I'm just going to write down a vector line integral just to be writing it down, I'm going to write it down like that. Right? Okay. Now, that said, let's not forget, this is also a perfectly valid way to write down the vector line integral. Notice it's a few more pencil strokes. Right? So, that's a downside. The nice thing about this formula is it's easy to compute. It is very plug and chug. It's a single variable calculus integral. That's really cool. Don't get me wrong, right? But again, to my earlier point, if I have the ulterior motive of I'm ready to proceed with explicitly calculating it, then yes. But minus that particular motivation, if I just want to write down an integral, this is easier. And then let's not forget we just talked about this notation. Now again, it's a little bit more to write down. So if I didn't have any particular reason one way or the other, I would usually not choose this. Right? But if you want to make the interpretation, if you want to interpret in the context of fluid flows, this is very natural from that point of view of fluid flows. So it's important to understand this one as well. All three of these notations are important to understand. And again, it's one of these situations where you can't just pick one and run with that exclusively. You need to understand all three of these bits of algebra, why they're equal, and why they're interesting. Okay. All right. And the reason they're all equal, of course, is because these three things are all equal. So, all right. Pause for questions before I go on to the next section. All right, good. Right, so let's talk about, by the way, you might even be able to guess. Let's see, we did scalar line integrals, then scalar surface integrals. Now we just did vector line integrals. Natural next thing to guess, vector surface integrals. And so that's our next section. There is a motivating physical application. Again, all of our integrals that we've written down, we start off with some physics problem, like how are we going to compute the mass in a solid, or how are we going to compute the work along a curved path? How are we going to compute, whatever. There's always some application that motivates our formula. So there is a physical motivating application here. The physical motivating application is something you might not have seen before. That's the weird thing about it. So the very first thing I have to do is talk a little bit about physics. Anyway, here we go. If you have a surface And if you have a fluid flowing along, and let's suppose that this is a 100% permeable surface and the fluid just can pass right through it. Right? Okay. So here's the fluid flowing along. And the fluid is represented by the vector field F. Keep in mind, the vector field is representing typically the velocity of the fluid flow. Okay. Question, what is the quantity per unit time of fluid that is passing through that surface? Now, flashback, way back when, chapter, oh gosh, what was this? This was, section 5.1, when we were first, 5.2, excuse me, we were doing first doing double integrals. And we considered this problem of water moving through a pipe. Y'all remember the water moving through a pipe? And I made the observation that, well, the total sort of flow rate, how much volume per unit time is passing through the pipe, I can break that up into little pieces. On each little piece, I can compute how much fluid is flowing through that little piece per unit time. And then the total flow, the total throughput, whatever you want to call it, volume per unit time going through that pipe is some summation that accumulates over that whole cross section. Okay. All right, so that's all this is. Right? I just want to know, now here we're not on a pipe, but we have a surface, and we've got a fluid flowing all over the place, and therefore to some extent through the surface. How much volume per unit time? How much is going through that surface? So we have a name for this. I laboriously did not use that word way back in 5.2. But anyway, here it is. The word is flux, which is a very, complicated sounding word. And that's all it is. It's no big deal. Flux is just how much fluid per unit time is going through your surface. Okay. All right. So, question, how are we going to compute that? One little detail that we do have to straighten out first, and this is minor annoyance, but here again is our surface. And we've got this fluid flowing through. And I want to know how much is flowing through. Well, I have to ask which way, right? So, is the fluid flowing, do you mean how much fluid is flowing like this through the surface? Is this the positive direction? Or, look, it's just as reasonable. I could say that, no, I'm not going that direction. I want to know, I've got this fluid and it's flowing along. I need to keep track of to what extent is the fluid flowing that way through the surface. Sort of, downward, you might say, through the surface. Just as valid of a question. Right? If the fluid is going the correct direction through the surface, then we call that positive flux. If the fluid is going the wrong direction, we just call it negative flux. Right? So we have to have a sense of, wait a minute, which way is the positive? Okay, so the way we describe which way is the positive is with a unit vector perpendicular to the surface pointing in the direction that we're going to consider to be the positive direction. So I'm going to call this the unit normal vector for the surface. A quick word of warning. That is a unit vector. It is, you'll notice I use lowercase n, not capital N. Right? Remember, capital N refers to in a parameterization. It's the perpendicular normal vector that you get from a parameterization. This does not come from the parameterization. This is completely, this has no idea you've even parameterized your surface. Maybe you haven't even parameterized it yet, right? So this is intrinsic to the surface. It is, very importantly, a unit vector. You got to be careful about this going forward. Awkwardly, back in chapter 1, when we were writing down the equation of a plane, we used lowercase n and didn't require that it be a unit vector back in chapter 1. Back then, little n was just any old vector, whatever vector perpendicular to your plane. Knock yourself out. Pick whichever one you want. Going forward, we really need this to now be a unit vector. Okay, so make sure that you're aware of that point. It can be really problematic. Does everybody see what I'm talking about here? Everybody see the concern? All right. Okay. Right. Okay. So how do we compute from this? First, I'm going to make an appeal about directions. Let me just come up to here. And let's look at this vector here. That's my field vector. And I've got this normal vector describing the direction. So that's my positive. That's telling me two things. It's telling me which way is the positive way through the surface, and furthermore, it's telling me what is the direction that's actually through the surface. I need that vector to be perpendicular to the surface. Right? Okay. All right. So the first observation I want to make is this field vector. I can think of it as having two components. The vector field, vector F, has a component, a part of it that is parallel to the normal vector. And then there's another part of it that is perpendicular. Perpendicular to the normal vector. Right? Okay, now let's think about these two components. Let's think first about the perpendicular component. That perpendicular component of the vector field. Let's, to what extent the fluid is flowing along the surface, parallel to the surface. And this is just a physical appeal, but the assertion that I'm going to make is that it doesn't matter. When it comes to calculating flux, I could not care less how much the fluid is flowing along the surface. Because along simply isn't through. Yeah? Does that seem plausible? So, we're just going to throw that part away, is the idea. Here's a different way to think about that, and just it's a silly metaphor, but metaphors are nice. Here's a reason you might be interested in flux. Suppose you're fishing with a net, right? And you've got one of those boats or whatever that's, holds this great big team of, I don't know how that works exactly, but suppose you've got this great big net down there, right? And so your net, let's say, is sitting in the ocean in some way, and the ocean current is pushing water through the net. Well, the idea is that there's a certain concentration of fish, and as that water goes through the net, the more water goes through the net, the more fish you catch. Right? So someone fishing with a net would be interested in the flux of the water through that net, because more flux, more fish is the idea. Right? So in this context, the reason why we don't care about that, the parallel component there, the part of the field vector that's parallel to the surface. If your net is like this, and if the flow of water is like that, you're not catching any fish. This is the silly way to arrange your net, right? And the fish just go right along, and they're like, oh, hey, check it out, there's a net down there. And they just keep right on going. They don't get caught. Does that make sense? Right? So the perpendicular component we're just going to throw away. And having thrown that away, it is this parallel component. This is so awkwardly, it's parallel to the normal vector, but it's perpendicular to the surface. So this is the part that we actually care about. Right? And so we're not interested in the magnitude of F itself. That magnitude of F itself includes consideration of how much the fluid's flowing parallel to our surface. It's silly, right? What we want to know is what's the magnitude of that perpendicular component, right? Perpendicular to the surface. So this is F perp. We want to know the magnitude of F perp. Okay. All right, and now I'm just going to make an appeal back to that question that we solved back in section 5.2, where, well, if you know the speed that the water is going through your net in the perpendicular direction and multiply by the area, that speed times area tells you the flow rate, what we called the flow rate way back then, what we're calling flux now. And so here's that formula. This is just in this new context, this is that old result that we got back in chapter 5, earlier in chapter 5. Okay. And then don't forget, by the way, the magnitude of that perpendicular component, that is F dot n. Dot products with unit vectors give you components, and that's exactly the component that we're interested in. Okay, is everybody on board so far? So here's our formula for flux. Again, this is a new physical concept, right? Now, when we started talking about work way back in chapter 1, I had to give you a little bit of a discussion of what is work, but we mostly went on to here's the formula, how to compute it. Well, so we've talked a little bit now about what flux is, and here's the formula for how to compute it. And now, just like we did in the previous section, we're going to say what happens if things aren't flat and things aren't constant. Right? When we were looking at work in the last section, instead of a straight line displacement, what if we have a curvy displacement? Instead of a constant vector field, what if we have a wambly varying non-constant vector field? How does that change things, right? And chop it up, add it up. So same question here. I want to ask now, suppose you have a non-flat surface. Well, your normal vectors are going to be different at different points on that surface. You can't just say, oh, yeah, just dot with the normal vector. Which one? Right? Likewise, what if the field vectors are not constant? It could easily be that the field vectors are wildly varying as well. They're not constant. Which one do you dot with which normal vector? Okay, so that is a hard problem. And the way we're going to address that, again, it's chop it up, add it up. So we're going to take our surface, chop it up in a bunch of little pieces. On each little piece, we're going to look at the flux through that little piece. On that little piece, that is approximately flat. Right? The field here, the field is approximately constant. Right? So on each little piece, we've got a familiar solution. We're just gonna do F dot n times area on each little piece, and then we're going to add up over the entire surface. So morally, it's the same chop it up, add it up strategy that we've applied in so many other contexts. And here it is. So again, no big deal, really. I mean, by the way, the notations here start to get kind of scary looking. If you if you look at them from the outside, I'm like, oh my gosh, wow, look at that. But it's the same idea. So chop it up, add it up. Right here, we're just, instead of chopping up little pieces of mass or little pieces of work or little pieces of volume, here we're adding up little pieces of flux over a surface. So chop it up, add it up, and then let's see here in that formula, flux is this, discussed on the last page. So on each little piece, F is approximately constant, N is approximately constant, the surface is approximately flat. So on each little piece, I can just say F dot N times area. Where is it? Here we go. F dot N times area. Right. And I get a new kind of Riemann sum. And again, this is what is this? Oh gosh, I've lost count. Single variable integrals, double integrals, triple integrals, scalar line integrals, scalar surface integrals, vector line integrals. This is now our 7th kind of integral. It's a Riemann sum. It's a chop it up, add it up, but the context is a little different than all of our previous 6 contexts. So this is now number 7, integral number 7, a vector surface integral. Here's our definition: a vector surface integral. This Riemann sum. The terminology, I think, is highly plausible, right? It's a surface integral because it's accumulating over a surface, of course. Vector surface integral because, well, our integrand is pretty obviously a vector. And we'll talk about that whole ds thing at the end momentarily. But vectors, there's different constructions. We'll call this a vector surface integral. The notation, delta S, ds, right? Who didn't see that coming? Perfectly natural guess. And then f dot n is, you just write as f dot n. You're accumulating this summation over a surface. So 2 integral symbols to indicate that it's a 2-index summation, subscript to indicate what the domain is. So I like to suggest, as I've done a few times before, I'll bet you could have guessed this notation based on our pattern of how we've done things in the past. Okay. That's a lot to look at. Scary to consider how we would compute this thing. Of course, we're not going to compute this going head on. We're going to compute this by being clever, and that'll be coming up soon. And how to calculate it. I've got another couple of minutes. Yeah. Oh, another little bit of terminology, by the way. Sometimes I'll call this vector surface integral. I'll call it a flux integral. It's a vector surface integral, but it's a vector surface integral that's used to compute flux. So that's kind of natural. It's a little bit fewer syllables, a little bit easier on the tongue to say flux integral. Okay, so another little bit of notation, and maybe this will be a good stopping point. Here's what we just wrote down. Right, that's our vector surface integral. And notice that even though that appears to be the differential, and this appears to be the integrand, notice you don't have to view it that way. And really, if you get right down to it, where does this normal vector come from? That normal vector comes from the surface. It's really more naturally connected to ds, which also comes from the surface. So I think it makes loads of sense, and this is, again, something I like to do. I think it makes loads of sense to group n and ds together, and then just for sort of notational convenience, let's give that a name. Let's call that the ds vector. And this is a very standard kind of notation. It doesn't have the appeal that the dx vector did back in when we were looking at vector line integrals. Dx vector was a displacement. It was very physically natural, right? This ds vector, it's a little harder to see how is this geometrically or physically natural. So that's disappointing. But one thing that's nice about it that you can say is everything here comes from the surface. The ds vector tells you everything you could want to know about that little piece of surface. And the f here is completely independent of the surface. That vector field exists, independent of the fact that you're only interested in it on the surface. Okay, so I like this notation. This is my favorite personal notation for vector surface integrals, aka flux integrals. Right? I like to write it like that. If you like, you can write it like this. They are the same thing. Perfectly fine. I will point out that this is a little clunkier to write down. This is a little bit more compact and lean, and that has a nice appeal. Okay, there's a good stopping point for today. So we will pick up here on Tuesday. Don't forget we have an exam on Monday. And see you then.